So in the last section, we talked about derivatives, and we talked about the formula for the definition of a derivative, which, let's go back, is right here, or no. Oh goodness. There's a huge typo in here. Okay, so go back to your notes because there's a huge typo here. I forgot this limit part here. Okay. Limit as h goes to 0. So go back in your notes real quick and change that for me. That should have a limit sign in front of it. Once again, if you're just logging in, scroll back in your notes and change that because it should have a limit in it. I wrote it with the limit everywhere else. I just did not write it with the limit at the very beginning right here. So there should be a limit sign there. So we talked about the definition of a derivative using the limit. And I told you that we were going to have a faster way to do this because right now the way that this process looks is like this. Finding the derivative requires a whole lot of algebra. Now, that all being said, you are going to have to use the definition of the derivative on a test and in the homework because there's going to be problems where you're specifically supposed to use the definition of the derivative. However, going forward after this section, and besides the particular questions on the test that ask you to use the definition of the derivative, going on beyond that, we are not going to be using the definition of the derivative. So you do need to know how to do it because there will be problems on it, but that's a really long way to find a derivative. And there's actually rules that make it a lot nicer. So let's talk about some rules that make this process better. Few basic rules. So first of all, notation-wise, I'm going to write something like this. Right? Where C is a constant. Oops, my head is everywhere today. Alrighty. This is equal to 0, where C is a constant. Let me write this down and then talk about what I'm saying here. This notation that I'm using right here, this d dx notation, if I say d dx of something, this means take the derivative of the something. So, for example, if I said d dx of x squared, this means take the derivative of x squared. Find the derivative. So just this d dx notation here, that d dx notation means to take the derivative. Right, so I'm going to be using that notation here. So if you're doing the derivative of a constant, that derivative is 0. So as an example, if I said take the derivative of 7, the derivative would be 0. Taking the derivative of a constant gives you 0. And this makes sense visually. If you think about what a constant function looks like, a constant function is just a line like this. It's a line, it's a straight horizontal line, and horizontal lines have no slope. So this would be something like y equals 7, the line y equals 7. And if we found a tangent line for any point on there, the tangent line is going to have a slope of 0. So the derivative of a constant is just 0. Here's where we start to love polynomials. If you're taking the derivative of a number, or not a variable raised to a number, you take that number and you put it down in front, and then you decrease this number by 1. So it becomes n x raised to the n minus 1. That looks a lot scarier when I write it in math terms than it actually is when we use it. So, for example, if I'm taking the derivative of x to the 6th, this 6 comes down in front. So we have 6x, and then we just make this 1 smaller. So 6x to the 5th. For the constant multiple rule, if you have a constant k, and by the way, if you're wondering why do we use c sometimes and k sometimes, typically we use c when it's a standalone constant, and we use k when it's multiplying a function. That's just mathematician etiquette, I guess. No particular reason. You could use any variable you want for a constant, but we typically use c as a standalone constant and k when it's being multiplied. So if you have a constant being multiplied by a function, then the derivative just has that constant out in front. So if you take the derivative of a constant multiplied by a function, you can just leave the constant alone and then take the derivative of the function. So let me show you that as a small example. If I'm taking the derivative of 2x, let's say, to the 4th, 2x to the 4th, we can take that 2 and move it out in front so we're not worried about it. So 2, and then just take the derivative of x to the 4th. So we'd have 2, the derivative of x to the 4th, using that power rule, bring the constant down in front, or sorry, not the constant, the exponent, bring the exponent down in front, and then lower the exponent by 1. And then 2 and 4 can be multiplied together to give you 8x cubed. Now, let me kind of talk real quick about what just happened. We can do it this way, and for the very beginning, we are going to do it this way, where we take the derivatives separately, but what really ends up happening, just kind of note this, when we take the derivative of this, what really ended up happening was 4 got multiplied by 2 to give us 8, and then we decreased the exponent on x by 1. That's not a coincidence, that is what is actually going to happen. I'll do it slow at first, but then we'll kind of get faster at it, and we won't write it like this. We're going to go immediately from here to here. And then finally, if you have two functions that you are adding or subtracting, and you're taking the derivative of them, the sum or the difference of two different functions, you can just take their derivatives separately. Hold on, I want to shrink him down a little bit so I can maybe put an example in there. So as an example of this, if maybe we had x squared plus x to the, let's do 10. And we're taking the derivative of that. We would take these derivatives separately. So the derivative of x squared, take that 2, put it down in front. Then subtract 1 from the exponent, and you'd have 2 minus 1 is 1, plus, bring the exponent down, and then lower the exponent by 1. Really, we wouldn't write the 1 as the exponent, we would just write 2x plus 10x to the 9th. But it's basically what you'd hope would happen, right? We would hope that, like, if you were just adding or subtracting two functions, that you could just take their derivatives separately and it all turns out good. Now, while this is true of addition and subtraction, this does not work with multiplication or division. In fact, the whole next section is the product and quotient rules. So essentially, if you're taking the product, so if you're multiplying functions or dividing them, we can't just take the derivative on the top, derivative on the bottom. There's a whole new rule that has to be used, but we'll get into that later. That's a rule for later. Let's just talk about our basics for now. So let's find some derivatives. Looking at this function, 3x to the 4th minus 5x cubed plus x squared minus 2x plus 4. Finding this derivative. So f prime of x. So this constant, 3, I'm just going to leave alone for now. And then, let's use green. For the x to the 4th part, I'll take that derivative. So I'll take his exponent down, and then I will lower his exponent by 1. So 4 minus 1 is 3. For the next one, minus 5, then for x cubed, take the exponent down, and then 3 minus 1 is 2. For x squared, take the exponent down, 2 minus 1 is 1. Minus. Now, here's where it's a little weird. So we have the 2. We're working right now on this one right here. Right? We're working on this guy. Where there's the 2. Technically, x is the same as x to the 1. So if you're taking the derivative of x, right, you bring the 1 down, and then 1 minus 1 is 0. Finally, the derivative of a constant, and just a constant alone, remember, was 0. So simplifying this, we have 3 times 4 is 12x cubed. 5 times 3 is 15x squared. Now, x to the 1, again, that's just the same thing as x. So I'm just going to write x. Minus 2, and now let's talk about x to the 0. Right? X to the 0, anything to the 0, is just 1. Anything to the 0 is just 1. So really it's just 2 times 1 is 2, and then x to the 0 is just 2, and then plus 0, that's plus nothing. So final product, 12x cubed minus 15x squared plus 2x minus 2 is our final answer for the derivative of 3x to the fourth minus 5x cubed plus x squared minus 2x plus 4. So a little note here we can make. Future note. The derivative of x ends up just being 1. Right? We took the derivative of 2x, we started with 2x, but its derivative ends up being 1, the x part at least, ends up being 1 because x minus, or 1 minus 1 is 0, so you end up with an x to the 0. And then we can kind of expand that further and say that the derivative of some number, I'm just going to put number times x, is just that number. So the derivative of 7x is 7. The derivative of negative 5x is negative 5. So you're going to actually end up loving polynomials. This process that we wrote here on an exam, by the time we get to exam time, if you're using derivative rules, this derivative, you just go straight to here, really. I mean, once you're good at derivatives, when I'm taking this derivative, I'm like 4 times 3 is 12, x cubed. 5 times 3, 15, x squared. 2 in front, x. 2x just becomes the 2, and it becomes a very fast process. But what about radicals? Well, there's a trick. You can rewrite radicals as exponents. Which is something we've done this before. So looking at our original function, so this is the original function, no derivative yet. I'm just rewriting it. The cubed root of t is t raised to the 1/3 power. The fifth root of t squared is t raised to the 2/5 power. Again, we have not taken a derivative yet. Now let's take the derivative. So this will be g prime of t, the derivative of g. So we take the exponent, we put it down in front, and then we're going to subtract 1 from the exponent. I'm writing it like this because with fractions, it's not, the mental math isn't as quick necessarily, so I'm just going to do it in a few steps. Plus take the exponent, so the 2/5, put it down in front, and then we'll subtract 1 from the exponent. Either using fraction math or a calculator, 1/3 minus 1 is negative 2/3. And then 2/5 minus 1 is -3/5. You do not need to rewrite it in radical form. You can leave your answer in the exponent form. You don't have to write it if you don't want. If you want to, for those of you who are like, no, I want to do that, the way that would look would be 1 over 3 square root t cubed plus 2 over 5 fifth root. Oops. Hold on. Mistakes. Don't mind me just making mistakes here. 1 over 3 cubed root of t squared is what this should be. Cubed root of t squared. And then this would be the fifth root of t cubed. But that would be if you wanted to. If you really just want to practice your radicals, that's fine, but you don't have to. Just some people like to go that little extra mile there. Can I answer any questions so far? We'll be doing more examples, don't worry. But can I answer any questions? All right. So before I had told you, multiplying functions together doesn't work the same way with derivatives. So I'll make the actual note here important. The derivative of two functions being multiplied together is not underline, not f prime of x times g prime of x. We will get a rule for this later, but for now, if you have something like this, where there's two functions multiplied together, you're going to have to multiply it all the way out before taking the derivative. Right, so for now, we're going to multiply out before we differentiate. So step 1. Multiply. So however you like to multiply, really what you're doing is this game, remultiply everything and it just becomes a mess. That's the game you're playing. I've talked in my other classes, there's different ways to multiply polynomials together. So for some people, the method they like to use, it's called the box method. And I am indifferent to which method you use. I'm actually going to set this up slightly different. I personally would just do this, but if you don't like that and if you feel like that gets a little bit messy, the box method of multiplying I'll take z squared minus 3z plus 1. And then the other polynomial is z cubed minus 1. And then you're just multiplying. So each square, it's like Battleship. So this square, you multiply these two together. So you'd have z to the 5th. For this square, you would multiply negative 3z and z cubed together. So you'd have negative 3z to the 4th. 1 times z cubed is z cubed. Z squared times negative 1 is negative z squared. Negative 3z times negative 1 is 3z. And then 1 times negative 1 is negative 1. If you have all the powers and they're all descending, it all turns out nicely and you can add diagonally. But here we can just see none of these will combine together. So we could just write, what is this? H of z is z to the 5th minus 3z to the 4th plus z cubed minus z squared plus 3z minus 1. And again, these are the same numbers you'd get from doing z squared times z cubed is z to the 5th. Z squared times negative 1 is negative z squared right here. Negative 3z times z cubed, negative 3z to the 4th, negative 3z times negative 1, positive 3z. You can see these are all the same things you'd get from distributing. So whatever method you want to do, that's just one method I've taught people and some people like it. Now we can take the derivative. So now we can differentiate. So I kind of mentioned this briefly in our last class. We are not deriving something. So sometimes students like to use this. They're like, we need to derive the function, but that wouldn't be the correct terminology to use. The terminology that we would use is we would differentiate a function. So to take the derivative is to differentiate. So we're going to differentiate this function here, and that will give us h prime of z. So why don't you quickly on your paper, take that derivative real quick, just kind of practice it. And then I'll put the answer. Oh, we'll go through it, but just give it a go. Right? So I'm going to do this one a little bit quicker, and I'm going to use the trick of multiplying the exponent and the number in front. So with z to the 5th, we should have 5z to the 4th, right? Subtracting 1 off the exponent, bring the 5 down. Then for this next one, 4 times 3 is 12, so negative 12. And then 4 minus 1 is 3. For z cubed, we have 3z, then subtract 1 from the exponent, so it's 3z squared. Minus 2z, and then the special rule we talked about for when there's no exponent is that basically the variable just disappears, so this is plus 3. And then the derivative of a constant is 0. So this would be our derivative. Can I answer any questions on that derivative? Okay. So for this next example, we have a similar situation to the one above, where we can't just divide the derivatives. So same as above, the derivative of two functions that are being divided is not, and I'm making this really bold because I'm going to see this mistake made on tests and it's going to make me cry on the inside, so I'm going to make it bold, is not just taking the derivative of the top and taking the derivative of the bottom. You can't just differentiate the top and put it over the differentiation at the bottom. So instead, what we're going to do is some fraction math. So what we know is if you have a plus b over c, this is the same as a over c plus b over c. Essentially, you can give that denominator to everybody, and that's what we're going to do. We're going to distribute the denom to each term in the numerator. So we have f of x is equal to x cubed over x minus 2 square root of x over x. For the next step, we're going to change any radicals into exponents, and then we're going to simplify. It's really important here that you note that I'm not putting a prime on these, all right? I'm not putting a prime there because we haven't taken the derivative yet. So if you're on your homework, if you're putting a prime on a step where you haven't taken a derivative, I'm going to take off points for that because you're saying that something's a derivative when it's not a derivative yet. It's really important in math that we are specific with our notation and that we mean what we write. So there's no derivative symbol, there's no prime because we have not taken a derivative yet. We are just doing algebra at this point. So x cubed over x, that's going to be x squared minus the radical, this is 2x to the 1/2 over x, right? So x to the 1/2 over x to the 1/2 minus 1, because you're subtracting that denominator. So ends up being x to the negative 1/2. So minus 2x to the negative 1/2. The 2 stays up top. X to the negative 1/2. And we're going to leave it as an exponent. So now we're okay to step 3, differentiate. So now I'm going to write f prime of x because I'm taking the derivative. So I have 2x, taking the exponent down, subtract 1 from the exponent, minus, right? Now we have 2 times negative 1/2. That would be negative 1. 2 times negative 1/2 would be negative 1. So really, this is going to turn into a plus, but maybe what I'll do is I'll write this down so that you're not confused in the future. So we are doing 2 times negative 1/2 here. And then negative 1/2 minus 1. So this whole thing right here is just going to turn into a plus sign because the 2's cancel each other out. It's just going to become a 1 and then a negative make a plus sign. So plus x to the negative 3/2. That is our derivative. Can I answer any questions there? So in these weird cases, you're going to need to simplify the fraction, and then you're going to do the exponent simplification until you're down to a point where you can use the power rule. Once you use the power rule, you're using the power rule to differentiate. So with this last example, same idea. We are going to first start by rewriting it because we have a fraction here and we want to rewrite fractions before we differentiate them. So we want to rewrite fractions or radicals, but in this case a fraction, in exponent form. Here's something to note. If you have 1 over x to the a, this is the same thing as x to the negative a, one of our exponent rules. So p of w, we can leave that first term alone, that 7/3 alone. And then instead of 1 over w to the pi, remember pi, and pi is just a number. Let me just kind of make a note on that. Right, it's the number 3.14. It extends forever, but it's just a number nonetheless. This is w raised to the negative pi. And then we can differentiate. So bring the exponent down. Right? 7/3 minus 1 is 4/3. You do want to start kind of getting good at this fraction math in your head. So just kind of quickly, if you're not great at fraction math in your head, because you can use a calculator, but it's just a lot more work. If you're subtracting 1, you're subtracting 3/3, and that's where you get 4/3, because you can combine the numerator together. But you can do this with like anything. If you have like 12/7 minus 1, you're really just, if you made this into 7/7, you're doing 12 minus 7. So it ends up being the numerator minus the denominator over the old denominator. 12 minus 7/7. So 5/7. I find that knowing how to do this fraction math in your head is a huge benefit, something you might want to practice. With negative numbers, just be a little bit more careful, like negative 3/5 minus 1, negative 3 minus the denominator over 5, that's negative 8/5. So you end up taking the numerator and subtracting the denominator. That's how you can do it quickly with fractions. All right, for this next one, taking the negative pi down, so taking negative pi down, we'll have a negative pi, w, and then now we have negative pi, and you need to subtract 1, but they can't simplify that anymore because pi is just a number. That's already as simple as it can get. So this would be our answer here. questions, concerns on this one? All right. So let's get a few more. Let's get a few more derivatives in here. Exponential and logarithmic derivatives. The two big ones that you're going to see most frequently are this top one and then the ln one. The other two are much less common. You'll still need to know their derivatives, but you won't end up seeing them as frequently as you'll see e to the x and ln x. Ln x in particular is going to become your best friend when we get into logarithmic differentiation, a bit different later. But both of these are very important. All four are important, but the two that are starred are very, very important. And the good news is this first one, the derivative of e to the x, is going to be your favorite derivative of all time because the derivative of e to the x is simply e to the x. You don't subtract from the numerator, from the exponent. You don't bring the exponent down. You just derivative of e to the x is e to the x. Now, if you combine that with the constant multiple rule, you get something pretty great, because if you're taking the derivative of a constant times e to the x, then it's just the constant times e to the x. So as an example, if you took the derivative of 2e to the x, it's 2e to the x. If you took the derivative of negative 4e to the x, it's negative 4e to the x. So having a number in front of the e to the x doesn't change what's happening. It still ends up being the derivative of e to the x. And that's pretty neat. That's a pretty nice derivative, if I do say so myself. Now, if you don't have e to the x, and instead you have a number raised to the x, and I'll make the stipulation in here, a needs to be greater than 0. That derivative becomes ln a times a to the x. So an example of that, if you're taking the derivative of 2 raised to the x, that derivative is going to be ln of 2 times 2 to the x. So e is the only one who doesn't have that ln a in front of it. And the reason why, if you're curious, the derivative, if we use this rule, the a to the x rule with e to the x, then you'd have ln of e to the x times e to the x, but ln of e to the x is just 1, so it ends up being e to the x. So technically, part A uses part B, but because ln of e to the x is just 1, you end up with this special property. All right, the derivative of ln x is going to be 1 over x. 1 over x. And then the derivative of log base b of x, kind of similar to part B, is 1 over ln b times x. So as an example here, if we have the derivative of log base 3 of x, that derivative would be 1 over ln the base is 3 times x. And once again, this part C kind of uses part D. So if you have, right, so first of all, something to know is that ln of x is equal to log base e of x. Right, so if you use this rule down here, the base is e. So if you did log base e of x, which is the same thing as ln x, and you use this rule, you'd have 1 over ln of the base is e times x, but ln e is just 1. So that's how you end up getting 1 over x. So part D does end up kind of using part C ends up using part D. All right, so let's put it to work. So we have y equals e to the x plus 2x cubed minus 7, the fifth root, 7 minus 7 times the fifth root of x plus log base 7 of x. We're going to start with rewriting y because we have a radical there and we don't like that radical. So we have e to the x plus 2x cubed, I don't need to change those, minus 7, and then the fifth root of x is x to the 1/5 power, plus log base 7 of x. Then we're good to differentiate. So y prime is equal to, the derivative of e to the x is just e to the x. For this next part, 2x cubed, 3 times 2 is 6. And then 3 minus 1 is 2. Minus 7 times 1/5 is 7/5. I'm just going to write that over here. 7 times 1/5 is 7/5. So it would be 7/5. And now use that fraction math that we were talking about before. 1 minus 5 is -4. So this becomes -4 over 5. For log base 7 of x, in this case, the b is a 7. So we have plus 1 over ln of 7 times x. For the next example, we have 3 ln x minus 21x plus 5. We don't have anything we need to rewrite, but for this guy right here, for 21 raised to the x, we need to remember we need to use the derivative of a to the x, where instead of a, in this case, a is 21. It's not negative 21. That's really important to know because a has to be positive, right? So it's like this. A is 21, not negative 21. Okay. So with 3 ln x, we'll put the 3 here, the constant multiple, and then the derivative of ln x was 1 over x minus the derivative of a to the x was ln a times a to the x. So this will be ln of 21 times 21 to the x. And that would be your full derivative. If you wanted to, you could write 3 times 1 over x as 3 over x. And if you really wanted to, you could like move the 21 to the x out front. Both of these are the same answer because multiplication order doesn't matter. And because 3 times 1 over x is 3 over x. So I think I'm going to take a moment. I'm going to give you some examples. You might need to grab another piece of paper. I want to give you some examples to try. I'm going to make some up. So I want you to take these derivatives. So maybe I'll do this. Here I'm recording now. 17 times 3 in my head is not happening right now. 51. 51x squared. Plus the derivative of x is just 1, and then derivative of 22 is 0. So that'll be our first derivative. For part B, you are going to need to rewrite it first. So if we do g of x, the cubed root of x to the 5th is x raised to the 5 over 3 minus 14x squared. And then 1 over x is the same as 1 over x to the 1. So this is minus x to the negative 1. And then we can differentiate. So we'll do g prime of x. This will be 5/3 x to the, so 5 minus 3 is 2, so this is 2/3. 14 times 2 is 28x. And then if you bring that negative 1 down in front, we're going to get a plus, and I don't need to put the 1 there because we don't ever put 1s in front, and then negative 1 minus 1 is negative 2. For part C, we need to rewrite and then simplify. So rewriting this, the square root of x, that's the same as x to the 1/2 over x squared plus x to the 5th over x squared minus x over x squared plus 4 over x. Then we're going to simplify, so we haven't taken the derivative yet. Oops, we haven't taken the derivative, so we're not going to put that prime there. So 1/2 minus 2 is going to be x to the negative 3 halves. 5 minus 2, that'll be x cubed. This is x to the 1st power, so 1 minus 2 is x to the negative 1. And then this is 4x to the negative 1. If you really wanted to, you could combine these together. So if you wanted to combine them together, because they are the same power, you'd end up with plus 3x to the negative 1. And now we can differentiate. So h prime of x will be negative 3 halves. X raised to the negative 3 minus 2 is negative 5 halves plus 3x squared. Negative 1 times 3 will just make this a negative sign. X to the negative 2. Now, if you didn't combine them together right here, if you didn't combine these two together, instead of having negative 3x to the negative 2, you'd end up with plus x to the negative 2 minus 4x to the negative 2 if you did not combine them together. So that's what ended up happening there. And then for part D, we're going to rewrite. So 1 over the 7th root of x, this is j of x, is going to be x raised to the negative 1/7, negative because it's in the denominator, and then it's the 7th root, minus 5, x to the negative 1/2, plus 18, x to the negative 9. Then we're going to differentiate. So we have j prime of x is equal to negative 1/7 x to the negative 1 minus 7 is negative 8. So we have negative 8 over 7 minus, well, it's going to be plus, right? Because we have a negative times a negative. 5 times 1/2 is 5 halves. So plus 5 halves. X to the negative 1 minus 2 is negative 3 halves. Not plus, this will be a minus because negative 9 times 18 will be a negative, and I'm not going to do that in my head because I'm not. Minus 162. X to the negative 9 minus 1 is negative 10. So let me kind of box all the answers here. How did that go? This might be a time where you kind of realize that maybe you need to do a little bit more refreshing with your exponent math, maybe your fractions. This might be a good time to do that. But in general, how are we feeling about those ideas, about the concepts? We're feeling good. It takes practicing. I don't know if anyone noticed, I posted an announcement like a little bit before class began, like a few, not even an hour, I think, before class began. I know I've heard comments from some people saying that they wanted more examples and stuff. And I know that the guided lecture notes aren't the same as a full-on textbook. Someone just said, I like working the extra examples. I think that helps, especially with something like this where it really does take some extra time. Sometimes examples are hard to come up with off the top of my head, but these extra examples are easy for me to come up with out of anywhere. Anyway, back to the idea of a textbook. So we don't really have a textbook for the class. We have the guided lecture notes, and I know the guided lecture notes aren't the same as a textbook. So OER stands for Open Educational Resource. There is an OER calculus textbook available. It's called Apex Calculus. Essentially, it's just a free textbook created by somebody who said textbooks are too expensive. I'm going to make mine for free. So I put a link to that textbook in the resources page and also in the announcement. So if you would like to have extra resources, that's one way to do it. The only thing you have to keep in mind is that the units in our guided lecture notes won't line up exactly with the units in the textbook, but you can kind of look for keywords. Like if you're looking for definition of the derivative, you can kind of scroll through till you find definition of the derivative. But it'll have extra examples. There are answers to all the odd problems in the back of the textbook that I posted. So hopefully that helps a little bit, especially for those of you who really feel that the textbook is a very useful resource to you. Originally, it's a lot easier to do this class in person. The original reason for no textbook is like, well, we're going to be in person. It's tends to be a lot easier to teach the concepts in person. And I also just like to not have students pay $150 for a textbook plus online homework access. It would have been nice this semester to have that online homework access, but at the same time, like, I don't want to cost you guys a bunch of money. It's not the time to be costing a bunch of money. So hopefully this open resource textbook helps. There's not a ton of them out there for calculus, but there is a few. All right. Are there any questions on this before I move on those examples? So I will move. So someone asked, is the textbook useful for Calc 2 as well? The textbook itself is, I posted chapters 1 through 6.1, but there's also, I believe, there's the other sections, and the other sections have, I believe, Calc 2 stuff. I'm going to double check right now. Where's their table of contents? Yeah, so there are other, so they have a second for the second half of the textbook that they have posted is all the Calc 2 stuff. So if you search for Apex Calculus, you can find their section 2 for that. I've never used Apex Calculus, so like all I've done is scrolled through it and said this looks like a good textbook. I can't vouch for it 100% since like I've never actually used it, but I think it should be pretty good. It looks like a pretty legitimate textbook. Kind of looks exactly like what you'd get in the classroom or for, $300 online on Amazon. All right. So, example 2.2.4, determine the values of x for which the function h of x equals 2x cubed minus 1/2 x squared minus 15x plus 3 has a horizontal tangent line. Okay, has a horizontal tangent line. Let me kind of underline that. Horizontal tangent line. This means the slope of the tangent line is 0, right? So like if you think of like a horizontal line, it has slope 0. So if the tangent line has slope 0, that means the derivative there has to be 0 because the derivative is going to give us the slope of the tangent line. So we want to find out where h prime of x is equal to 0. Right, so finding h prime of x, 2 times 3 is 6. So we have 6 and then x squared. 1/2 times 2 is just going to be 1. So you don't need to really write that. 1/2, it's just going to be minus 1 and then x. And then the derivative of 15x will just be minus 15. And the derivative of 3 is 0. So we found the derivative. Now we want to set the derivative equal to 0 and solve for x. So we have 6x squared minus x minus 15 equal to 0. Whatever your favorite method of factoring these are, I will once again quickly do the bottoms up method for anyone who wants to see it. I don't care how you factor these, whatever your method of factoring is. The bottoms up method is the method that I like to teach because I think it's a cool method. Don't have to use it. I'm only going to explain it briefly. I've explained it before, but I'm just going to explain it briefly. Essentially, you take your quadratic, and then you take this guy and you multiply him there. So 6 times negative 6 times, we'll just do 6 times, well, negative 15. 6 times negative 15 is negative 90. You do that, and then you get rid of this number out in front. So you have x squared minus x, and then you take this negative 90 and you put them right there. So you replace that last number. This 6 is gone now. You can factor this. So this is going to factor into x minus 10 times x plus 9. Then the 6 comes back and it goes underneath these numbers. You simplify as much as possible. So x minus 5/3, x plus 3/2, and then you bring the bottoms up. So you take the denominator and you bring it up front. And you get 3x minus 5 and 2x plus 3. Once again, I don't care how you factor. You need to know how to factor. Factoring is very important, becomes important for the rest of your math life. But it's another quick review of the bottoms-up method, which is a really cool method. I think it's really, really neat. Moral of the story is that this factors into 3x minus 5 times 2x plus 3. And I know we've talked about factoring on the first day, but I'm always going to bring it back up. Right? So we just have to solve for these x values. So if you have 3x minus 5 equal to 0, you get x equal to 5/3. 2x plus 3 equal to 0. X is equal to negative 3/2. So it just says the x values. It just wants the values of x. So we don't need to find points or anything. So we have 5/3 and negative 3/2. Those are going to be the x values where the tangent line is horizontal. For example 2.2.5, find the equation of a line tangent to the curve f of x equals 3x squared and has and perpendicular to the line 3x plus 18y equals negative 7. So there's a lot here, right? We need to know what slope we're looking for. So our first real issue is step 1. What slope are we looking for the tangent line? I hate when I have the word for together twice. What slope are we looking for the tangent line? Because when we know that, then we know that f prime of x has to equal the slope, and we can find the x value where that happens and the y value where that happens, and then we're able to find the equation of that tangent line. So finding the equation of a tangent line requires an x value, a y value, and a slope. We know that the tangent line is perpendicular to this line. So we can find the slope of that line if we can find the slope of this line, and we can find the perpendicular slope. So taking 3x plus 18y equal to -7, we're going to solve for y. So we subtract x, the 3x on both sides. 18y equals -3x minus 7. Divide both sides by 18. So we have -3 over 18x minus 7 over 18. Simplifies to -1/6 x minus 7 over 18. This is the slope of that's the perpendicular slope. The symbol for perpendicular, by the way, is an upside down T. So the slope that's perpendicular to -1/6, remember you flip the fraction and then you make it the opposite sign. So we know that our tangent line is perpendicular to this line. So we find the slope of that line, and then we find the perpendicular slope, and that's the slope of our tangent line. So for slope, we have 6. We need to find x values and y values now, and we're going to need to use the derivative to make that happen. So we have this curve, and I had set up here, we want f prime of x to be this slope. So we want the tangent line to have slope 6. So for our next step, we're going to find f prime of x. Oops, step 2. Find f prime of x. Then set f prime of x equal to 6 and solve for x. Right? Because we want to know which x values have a tangent line that has slope 6. So f prime of x, multiply 2 by 3, you get 6x. Now we set it equal to 6. So we have 6x is equal to 6, which means x is equal to 1. We now have the x value. Value equals 1. So when we go to use this in the line, we're going to have x1 is equal to 1. To get the y value, which is the only thing we're missing, you plug back into the original function, not the derivative, the original function. So our y value comes from doing a 1 plugged into f. So that's this function right here, 3x squared. So 3 times 1 squared is 3. So if y1 is equal to 3. And then the last step is to all put this into the equation of a line. So y minus y1 is equal to m times x minus x1. Plugging it all in, we have y minus 3 is equal to 6 times x minus 1. Distribute the 6, you get 6x minus 6. Subtract or add the 3 on both sides, and you get 6x minus 3. That is the equation of the line that's tangent. It's tangent to this curve and perpendicular to this line. Can I answer any questions on that? So for this next, oh, wait, he added stuff to the notes. Thought the next one was going to be a velocity one. All right, so another example. 2.2.6, find all tangent lines to the curve that pass through the point 3, 8. A graph of f is provided below. So we want to find all lines tangent to this curve that pass through this point. And by passing, the tangent line has to pass through the curve. So like, I mean, this is not a perfect picture. But it's kind of like you have a tangent line and it needs to pass through this point right here. This is the point 3, 8, which not very accurate looking from the picture because it's all stretched out, but that's the point 3, 8. Right? We want to find all lines, all tangent lines to this curve that pass through this point here. So this is going to require a bit of trickery. We need to find a point here on this curve, and we need to give him a coordinate point. So oftentimes we use x and y, but because we have x being used as a variable, we're going to use, I think, let's use a and b. This point is the point a and b. A comma b is the point that is on this curve and it goes through this point. It is the point where, let me write this down, a comma b is the point on the curve f of x that has a tangent line that passes through the point 3, 8. But here's the thing about a comma b. A comma b is on this curve 3x squared plus 12x minus 7, which means the y value b is actually just what happens when a is plugged into this function. So really, b should be f of a, because the y value of any point on this curve is going to be the x value plugged into the function. And well, that's interesting, because now what we have, f of a is just this function with a plugged into it. So we have 3a squared plus 12a minus 7. So now we've got to think to do what we're going to do with this information. We have a point. We have a point that the tangent line should pass through. And we have to, what are we going to do here? There's a few things. The first thing we can do is we can find the slope of this line, kind of. We can kind of find the slope of this line using the using the slope formula. Not using the derivative. We're going to use the slope formula first. Keeping in mind that this point down here we have relabeled as a comma 3a squared plus 12a minus 7. So the slope formula is m equals y2 minus y1 over x2 minus x1, just the regular slope formula. Doesn't matter which one you choose to be which. I'm going to go ahead and choose these guys to be my first ones. So x1 is a, y1 is 3a squared plus 12a minus 7. And then this guy will be my second point. So x2 is 3 and y2 is 8. And up to this point, no calculus, right? No calculus used yet. So y2 is 8 minus y1, 3a squared plus 12a minus 7. On the bottom, x2 is 3 minus x1 is a. We can simplify this. So distribute the negative. Negative 3, 3a squared minus 12a plus 7. Over 3 minus a, and then we can just combine. So minus 12a, 3 plus 7 is 10. Over 3 minus a. I'm trying to decide if the top one factors or not. I'm just going to plug it in to see if it factors. You can plug in, I'm trying to see if a minus 3 is a factor of this, so I'm plugging 3 into this to see if I get 0. Nope. Okay. We're going to leave him alone for now. The next thing, let's use calculus now. So we've done the slope using the slope formula. Maybe come back to this. Now, we can find the slope of this guy, right? We can find the slope at the point A, comma B. We can find the slope at x equals a by taking this derivative and plugging it in to the, plugging a into the derivative. So we're going to find f prime of x, and we'll plug in x equals a. So we're finding this slope in 2 different ways. Trying to keep it on the screen too. So f prime of x is 6x plus 12. F prime of a is 6a plus 12. You might think, oh, sorry, somebody said, oh, sorry, I didn't even look at the chat box. The 8 would make it factor, so, chat box, thank you. This is an 8. 8 plus 7 would make this a 15, and it'll factor, but it won't cancel, but it will factor. Because it won't cancel with the denominator, because it's going to factor into, because it won't it will factor with the, hold on, because that's a -3. So, okay, that changes everything. Not changes everything, it'll just make our life a little easier. So factoring that -3 out, you'll have a squared plus 4a minus 5. Oh, it won't, so nothing will cancel. No, nothing will cancel, but let's do it anyway. And this would factor into a plus 5, a minus 1 over 3 minus a. So nothing will cancel there. So if something canceled, that would have been really nice, but nothing cancels there. But it does factor, and that is important to know that I made a mistake right there, because that would actually changes everything. But here's the tricky part. So this is a problem in my UW class. They would do this problem on the second week of class, and the teacher always had to go over it because this is a trick, right? The trick is that you're using the slope formula, and now you used the derivative. And here's the tricky thing. These have to be the same thing, right? This slope and this slope, which I think we're going to end up using this guy and this guy have to be the same thing. I'm going to box this because this is going to be the one we end up using. They have to be the same because it's the same slope. So we can set them equal to each other. So f prime of a, which is the slope at a, and m, which is going to be the slope of that line, they're both the same slope. Those have to be equal to one another. So it'll make more sense why I'm going to leave it unfactored. If it canceled, I would use its factored form. It'll make more sense why I'm not having it factored once we do this. So we can set them equal to one another. And now we can actually solve for A. So we're going to have to do algebra to solve for A. Maybe I won't even write that step. I'll just do it. So to start with, I'm going to multiply 3 minus A on both sides, because when I do that, it cancels out my denominator. And then multiplying out the other side, we have 18A minus 6A squared plus 36 minus 12A. I'm going to move everything to one side. So first of all, 18A minus 12A, maybe I'll just write it. Let's not be cheap here. Let's write out every step. Negative 6A squared plus 18 minus 12 is 6A plus 36. Oof, we're almost there. Now we're going to add everything. We're going to make it so that one side is 0. So we're going to move everything over. So plus 6A squared plus 6A squared minus 6A minus 6A. And the reason that you don't want it factored here is because you would have to FOIL it back out so that you could move everything over. Minus 36. So you end up with 3A squared minus 18A minus 15 minus 36, negative 21 equals 0. Factor 3 out. A squared minus 6A minus 7 equal to 0. Here we go. Here's the factoring. A minus 7, A plus 1 equals 0. A equals 7, and A equals negative 1. Zooming out here, we're off the page. Now we're supposed to find all tangent lines to the curve. So to find these actual tangent lines, these are the x values right here. Oops. To find the rest of the tangent line, you're going to need the slope, which you can use this formula for, right? And then you're going to need the y value, which you use the original for. So for x equals 7, the slope is equal to f prime of 7, which it's just plugging 7 into this. 6 times 7 plus 12. So 42 plus 12, 54. Then the y value you get from the original function, which you can secretly see right here. 3 times 7 squared plus 12 times 7 minus 7. And I'm lazy enough that I'm definitely not doing that in my head. So that tangent line, y minus 224, that's y minus y1, is equal to 54 x minus 7. And then you could FOIL it out, whatever. I'm going to kind of go a little bit quickly here because I want to get through this. And then for the other one, x equals negative 1, finding that slope. The thing is, it can be different. So f prime of -1 equals 6 times -1 plus 12. So -6 plus 12 is 6. For the y value, plugging back into the original function, 3 times -1 squared plus 12 times -1 minus 7. So we have 3 minus 12 is -9, minus 7 is -16. So y plus 16 is equal to 6 times x plus 1. Without writing down all the steps of what this would be, this would come out to be y equals 54x minus 154. And this one over here would come out to be 6x minus 10. Oof. So there it is in all its glory, which unfortunately doesn't give us time to go over the next problem, but that's no big deal. We can catch that, and we can catch that before the next section. I do have a ton of one-on-one meetings scheduled for my other class. I have, oh goodness, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 back-to-back meetings apparently scheduled for the next 3 hours of my life. So I'm going to get going right now so that I can stretch, do some jumping jacks, and drink some water before sitting down for 3 hours of meetings. So I'll let you go a few minutes early, but this is the easier way to do derivatives. Most of it, I mean, this right here is just problem solving, which is fun. But there's that. Remember, your test is due on Friday. It's due on Friday. Please make sure that all your work is neat and tidy, easy to grade. I'm hoping to have your homeworks graded soon. This week is very, very crazy for me. I've kind of explained earlier. I have all these one-on-one meetings, and I had 70 plus tests to grade in my other class, and my tenure binders due this weekend. So things are kind of crazy this week. I'm hoping that I get your homework 3s graded and back to you soon. I'm hoping to get that done by Friday. Sorry, I can't have it done sooner, but your exam is due on Friday. If you have questions or concerns, send me an email. Otherwise, have a fantastic weekend, and I will see you on Monday.